Welcome, let's get started. Let's talk about algorithms. Okay, a little of my background. I thought I was the newest Flink committer. Actually, we have a new committer, but I've been a committer for about a year now. I think actually about half a year, sometime in February, I think. My background, we used to write our code in Hadoop MapReduce, and I was evaluating frameworks. I was looking at Spark, and I came upon Flink. It was around the time that Flink was kind of in the news, and found that the Flink API was very similar. Some of the Flink ideas were very similar to what we saw in Hadoop, particularly with the tuples, the operator reuse, the efficiencies of MapReduce, and the scalability. And I was also drawn by, of course, Spark and Flink having a fluent API and even being able to add operators. And then kind of I stuck with it, meeting all of you and meeting the team online. It's been really nice to contribute to a project. So most of my commits have been performance and stability, small features. And I've also done a lot of work with Jelly and adding some of the capabilities we'll talk about in a few minutes. All right, so first we'll review a little bit about graphs with Jelly. We'll review some of our new native algorithms, talk about some of configuring Flink at scale, my experience trying to run sort benchmark recently, and then we'll talk a little bit about profiling and benchmarking, and then last talk about some new features that I hope we can get it into Flink soon. Okay, so first, Flink is very popular with streaming. With Jelly, we use the batch API. So one question, I think Stefan actually answered this in the first keynote. There's a lot of overlap between streaming and batch. And the performance that we see, the performance improvements that we see in batch kind of bleed over into streaming. And the second point I'd make is that, well, benchmarking is in essence batch. I had actually written that before Stefan's comment. But anytime we're benchmarking, we're doing a bounded computation. And that's really just a batch process. What Jelly, I think, provides to Flink is a diverse set of scalable algorithms that allow us to really stress the Flink architecture. We've actually come across a lot of limitations and even some bugs just streaming through the massive data sets that we can produce in Jelly and being able to contribute back those bug fixes. So just a brief overview of what is Jelly. I know Vasi did a full talk at last year's Flink Forward. So a graph is just two data sets, a data set of vertices and a data set of edges, and those are bound by the common label type K. A vertex is simply a label and a value, a generic type, and an edge is simply two labels and a value. And there's been some talk recently about maybe having a bipartite graph, a bipartite edge, so we'll see if that gets in soon. Flink also has, Jelly also has a way to read in graphs. And we have some operators on the Graph API, although I don't know how much those are really used for writing algorithms. Jelly also ships with these iterative models to help it kind of emulate systems that users are used to, kind of Pragal style, the vertex-centric. There's that. I see these as the 1 function, 2 function, and 3 function iterative models. So we have several algorithms that are written in those. And then the part I've been working on kind of comes out in 4 parts. So the first is, can we generate graphs? Primarily, I play with RMAT graphs. We also have some interesting graph types that allow us to just stream through and perhaps test worst case scenarios on specific algorithms. I kind of just walk through the Wolfram pages and look for interesting graph types. We've also built out a set of composable building blocks. These are mostly for degree annotation, which is used for numerous algorithms. We have ways to simplify graphs. If you have duplicate edges, duplicate vertices, and then also ways to transform graph types generically. We've added a collection of algorithms, but also added this idea of an analytic that we'll talk about. And then lastly, there's this idea, I think one of my first commits was how can we take a data set and validate it, and actually discovered later that TerraSort with Hadoop had essentially done the same thing. So what is RMAT? Just a brief overview. It came out of Carnegie Mellon. The idea is to create a power law degree graph, purely generated, and they talk about parsimony, about just having a few input parameters, building a community structure. So the basic idea is you have 2 to the n vertices, you get edge factor times vertices edges, and you can feed in these different bit probabilities. That gives you your data skew, that gives you your power law degree. I also have some extra features. I've never really used these features. One last slide. So we know what a vertex is, we know what an edge is, it connects 2 vertices. An open triplet and a closed triplet, these are triplets. There's some disagreement in the literature about this. A triangle is a closed triplet, and an open triplet is obviously open. And then I actually have an algorithm to compute triads, the triadic census. A triad is any 3 vertices in a graph. So that's the distinction there. So what are the kind of graphs we can play with? So I ran through, we have a graph metrics algorithm now. You can put in any data. Sorry, I'm not talking about any real data today, but it was easier this way. So these are generated graphs, but if you plug through your own data sets, you can then see what does your graph look like. We see that we very quickly scale up to trillions or even quadrillions of triplets. Billions of vertices, billions of edges, and essentially petabytes of data. So we can easily generate any volume of data that we want to play with. And you'll note here, so triangle triplets, we'll talk about in a few minutes. We can see that it's about 1/20th to 1/80th of the number of triplets. Okay, a few algorithms. So clustering coefficient, I worked on this for a while. We have directed and undirected versions of both local and global clustering coefficient. Measures the connectedness of a neighborhood. So it gives you a ratio between 0 and 1. You can think about this as how much does your neighborhood look like a clique? How much does it look like a tree or a star graph with no neighboring connections? And we'll note here that if a vertex has 2 neighbors, a connection between neighbors forms a triangle. So essentially, clustering coefficient is counting triangles. And we see that in the formal definition. The interesting part here is when the number of potential triangles is the degree you choose 2. How many pairs of neighbors do we have? And when we look at the global clustering coefficient, we're counting triangles over the entire graph, and comparing that with the number of connected triplets, number of triplets of vertices in the entire graph. Okay, so we have a very clever algorithm for enumerating triangles. This was the source that I could find. I'm not entirely sure where this came from. And the basic idea here is we want to join every edge in the graph against the set of triplets in the graph. So if we can enumerate all triplets, we already have a list of edges, we can join on those 2 fields and we find all triangles. And that's what the naive algorithm would do. But a much more efficient way to do this is to look at only where U has degree lower than V and lower than W. And that gives us a tremendous reduction in the amount of data we're processing. So one of the features we've added, and I'll demonstrate this through clustering coefficient, is implicit, that should say implicit operator use. Sorry about that. So here is the driver for clustering coefficient. It's running 2 algorithms. We have the global clustering coefficient as well as the local clustering coefficient. And we see them both together. We're also generating the graph. So these are actually called independently. And you'll find that with Flink, we can set up multiple outputs and run it in the same job. So we're actually overlapping our operators through implicit reuse. We're not explicitly exposing those operators. And it's interesting. So we can see here what's missing under local clustering coefficient is what is the extra for global clustering coefficient. So it's doing two things. One, it's looking at the degrees of vertices to compute that degree choose 2. And it's also counting triangles here. And then the local clustering coefficient is chopping up triangles, counting them, and then joining back with that degree to compute the ratio. So it's kind of progressed in 3 generations. The first, when I was just programming it myself, the idea was I would just explicitly expose any data sets that I knew that I would reuse. The second is actually in Flink 1.1, was using code generation, which is the fad these days. But there were some limitations that I couldn't actually overcome in Java. And actually it turned out I was having classes try to represent. If you ever change the class, Java would complain. So in Flink 1.2, we fixed this. We had to go and we added a no-op operator, which actually acts as a placeholder for the preceding operator that we can then swap out. And I think I'm interested to see with SQL, with the Flink SQL API, the table APIs, with the code generation there, the operators that are now generated in code as we translate from SQL, to see if we could maybe reuse this capability. That if someone's writing, if people are writing similar SQL queries, if we could maybe go in there and reuse those operators instead of creating new operators. So how does this work? So what we do is we have graph algorithm wrapping data set. So if you return a data set, you extend this class. If you're returning a graph, you extend a slightly different class. And what we do is we define a mergeable configuration. So we can't do it automatically because the user's operator could flip a coin, right? We can't know what's going on inside the operator. We can't implicitly, even if it's configured the same way, we can't know that it's going to act the same. So we have to allow the user to choose whether 2 operators can be reused. And that's how we do that. This idea of a GraphAnalytic, which is very similar to when you call count or collect on a data set. What's happening is it's retrieving either the data set, all the values in the data set are being returned through an accumulator, through a list, or count is returning it through an integer. So the idea here was when you call count or collect, you execute your program. And we want to compose these algorithms so they can run at the same time. So we can't have collect calling execute for the user. So what we do is we allow the user to call execute. So anyway, this is actually allowing the user to call the GraphAnalytic as they would call count. You can call collect on it. The basic idea is we're going to run it, and then when we say get result, we're going to fetch the result from accumulators. So we've broken that apart into 2 operations. The first, we set up the output formats where our accumulators run, and then separately we call get result, where we can actually fetch the result. So to go over some similarity measures, this is our second set of algorithms we'll look at. So the most basic similarity is common neighbors. If you go into Facebook and they tell you look at someone's page and they tell you how many friends you have in common, that's common neighbors. It's a simple count. Jacquard's similarity makes that a ratio between 0 and 1, dividing by the number of total neighbors that you share. And then we also have atomic adar, which weights lower high degree neighbors. So we can imagine maybe the very high degree node could skew the data set. So we want to compute the inverse log to reduce that weighting. So how do we compute common neighbors? So some basic pseudocode. we take our edge list, we group on the source, we do something that doesn't exist yet in Flink, we call it cross group, which emits the neighbor pairs. We group on neighbor pairs, and then we add up how many of those neighbor pairs are present. So we can see here that in the star graph, each pair of external neighbors shares the common root node. So how would we perform a group cross? This has been talked about on the mailing. It's actually a very old ticket that never got implemented, but I think we have some interesting ideas to make this very fast and to prevent data skew. So this actually came from the ticket. This was Fabian's comment. So we want to do a pairwise combination of all elements of a group. So our current options for this are to group reduce, which requires the user to store all elements. And of course, users are limited in the memory they have. The second option is to do a self-join, which duplicates the amount of data transmitted over the network. So neither of those are optimal. So we can try a grouped cross, which isn't in there yet, but a flip will be out soon. Okay, so what's the issue? The issue is that when we do a cross product, we now have a quadratic explosion of pairwise elements. So how can we solve this? So what we end up doing is we end up slicing our matrix with fixed width slices. So each slice now is linear in the degree, right? 64 times the number of neighbors. So this, we've now taken our quadratic computation and made it linear. Unfortunately, generating these slices is still quadratic. So that's step 3. We need to perform 2 steps. This is what we do in our algorithms currently. This is how we operate. We do this in 3 steps. The first step, we emit the number of slices. So these initial elements are emitted into 1 slice, 2 slices, 3 slices, and finally 4 slices. And the second stage is that for our count, we emit the element into each slice. Now, Jacquard index and Damokidar are very similar. We just need to do a little bookkeeping. With Jacquard similarity, we need to track the degree of the target edge, and with the Damokidar, we're computing the inverse log of the source vertex. And the rest of the algorithm is entirely the same. Okay, some optimizations that we do. I like to say we should think like an element when we serialize in Flink. If you've seen Gabor's talk about serializers and comparators, serialization and the comparators are probably the hottest of the hot code within Flink and the most important to get right. So an example here from MapDriver. All MapDriver does when you look at it, it reads a record, it keeps a counter, and then it calls your function and outputs the record. So compared to other systems where outputs are kept in memory, even with iterative processing, Flink is always serializing data as quickly as possible. So we always try to use our basic types, things like integers and strings, rather than lists and hash sets. Flink provides these value types, and we're currently working on getting some value array types to efficiently serialize lists, and I could see doing value set or value other types of optimized data types. So a lot of times we talk about memory. I copied this from Wikipedia. We talk about being memory bound. We talk about I/O performance, but main memory is actually very far down the hierarchy of memory. So efficient serialization allows us to keep Flink's data up in the hot code, up in CPU cache. Object reuse. So we always, every algorithm that we write, we try to reuse objects. We always try to go in there and enable that by default. It can be a little tricky, but it's worth it. I don't actually have any hard numbers on the performance benefit. I know when there was an issue, there was a limitation early on that we weren't reusing objects, and we got a 5% improvement by simply tying that together. Things to watch out for is that if you're going to hold on to an object, you need to make a copy. And if you're going to output it, it might be changed if you have any chained operators. There is some discussion for reworking object reuse. Rather than enabling having a global configuration, having annotations on individual operators, which would allow us to flag that our code that we've written can reuse objects, even if it's composed into algorithms that aren't, with other operators that aren't reusing code. So how do we make copies of our data? So to use in Jelly, we want to support essentially string, int, and long are the three types that we typically use for labels, but potentially a user could use any type. We always program to generic interfaces. So we require that our types be copyable values, which has been in Flink for a while. So our typical workflow is that if we don't have a copy, we can create a new copy. And if we have a copy, we can copy into the data field that we already have. It's also a good idea to annotate either with forwarded fields or to use the proper combine hints hash. A hash combine is a recent addition to Flink. I think it just came out in Flink 1.1. And this allows us to use an in-memory hash table rather than spilling to disk. We've seen improvements. I don't remember the exact numbers. I probably shouldn't say any exact numbers. But rather than sorting the full data set, we can create a hash table and simply update in place the results. And of course, the join hints, when, for example, we're joining edges on triplets, we know that we have far more triplets than we have edges. So we can do a repartition hash join, which will create a hash table of edges, and we can stream in our full set of triplets against that, never spilling to disk. So some configurations at scale. So Amazon Web Services, I work with Amazon Web Services. So my instance of choice is the C4. This is their modern compute instance. They have 36 it should say virtual cores. That must be a change there. 60 gigabytes of memory. We can push 800 megabytes to the Elastic Block Store. I've rarely seen Flink I/O bound. We're always CPU bound. I know Gabor, I think, mentioned this as well. Flink is typically CPU bound at this time. We get 10 gigabits of networking and an extra 4 gigabits dedicated just to EBS. Now, one issue we're seeing now is we have multiple NUMA nodes on a single instance. Right now we have 2. The new X1 instances have 4. So there's the idea of having NUMA support, essentially creating multiple task managers, each bound to a single NUMA node. So we're looking to get that in at some point. The optimal configuration actually is to use multiple disks. And of course, Flink has support for temp directories on multiple disks. And the most important parameter, I know Amazon wasn't able to speak today, but for EBS, bumping this I/O size to 128 kilobits, which is the max size, allows us to drive the max. That allows us to drive the 800 megabytes to the Elastic Block Store. The cost of this, we usually pay about 50 cents an hour with the spot pricing. It's best on nights and weekends when probably no one's using Amazon Web Services. For the memory allocation, so if you read the Flink documentation, they say to give as much memory as possible to the task manager. I actually found this is a limitation. The biggest issue with running out of memory, if you give all your memory to Flink, you'll have no memory for read-ahead buffers when you spill to disk. So the operating system, as you're reading in your hundreds or thousands of files, is pre-caching default 256K for each file. And so it turns out as we scale up to larger clusters and more spilled files, we actually want to reduce the amount of memory that we give Flink and leave a few gigabytes for the read-ahead buffers. We typically also drive this down the ratio to, well, we drive it up to 0.9 and give ourselves about 10% of the memory. I've never seen this be a limitation. And by using object reuse and limiting our impact on the garbage collector, we're able to reserve more memory for the task managers. So this is typically what I run with. So the important ideas here, like I said, we drive memory fraction about 0.9. We always like to go off heap. And because we're running on solid state disk, I would actually like to see a max fan. This is the number of files that we can read in at one time. I would actually like that to be infinite. There's no upper limit that I've seen on the number of files that we can do a sort merge on. So one other issue that's come up is how do we configure network buffers? And there's a heuristic given in the documentation. It's basically slots times the number of task managers times 4. I've seen no rhyme or reason to this number. We just recently added to the metric system available memory segments. And I think the best way to look at this is just to actually run an algorithm and monitor that value and see what you get and tune that way. Because this doesn't really scale linearly with the number of operators that are running. And I'm not sure, this may actually show up in the web UI. I copied in here what I use from a simple statsd server if I want to introspect metrics as they're coming out of the system. One limitation we run into as we scale up is that if we have the same parallelism for every operator, we run out of network buffers very quickly. We can see that we're very quickly giving gigabytes in between each operator just to network buffers. So we've introduced this idea of little parallelism where we keep the full parallelism for the largest portions of our job, but we scale that down at the, say for graph generation, we're only processing a little bit of data. Sort benchmark. So I recently attempted this. We didn't win. They haven't published yet, but we didn't win. That was the big result there. But it was fascinating to see how does Flink work sorting 100 terabytes in a public cloud. So that is cloud sort. Sort 100 terabytes as cheaply as possible in a public cloud. They define it as an I/O benchmarking, so they don't allow you to do things like compress. And the input and output have to be on persistent storage. That's something like Amazon S3 or Google Persistent Disk. And you can't use spot pricing. You can request spot pricing, but you can't use that for your final price. I find it very interesting. Amazon has much better compute. Google has much better networking. It'll be interesting to see how that changes over the years. So I published everything at my GitHub repository. So hopefully if anyone's looking at this in the future, it's soup to nuts. So everything from everything from input generation to output validation. I try to keep everything using kind of shell commands, Linux commands, so that we could reuse this in the future rather than kind of hard coding everything into a specific framework. Anyway, it's not a very interesting read, but if anyone's ever attempting this in the future, I think it would be a good starting point. And I listed here our final price. We're just over half of the prior champion, but apparently someone came in a little lower this year. It's interesting to see that the compute cost, most of the cost, is actually in compute, and our storage costs we're able to reduce significantly, but the network limitations for Amazon. Amazon actually throttles your connection to Amazon S3. So we're getting about half of the bandwidth, half of that 10 gigabits. So maybe we could have won if they hadn't throttled us. I was actually told Netflix has had issues with this, where Amazon, if you transmit too much over their network, they start throttling you, and that was something I had seen. It's also interesting when you see the spot pricing spike up, and you know that it was you that caused that. So a couple of things we ran across, well, I ran across. So the first issue was Java's SSL performance. I know we're talking about adding security to Flink. So this was, the first idea was, okay, I'll just use the Hadoop capabilities that Flink has and stream in files that way. And it was taking about 50% of the CPU was just doing the SSL. First, it was doing this counter mode, which I was able to disable, but you can't get rid of the SHA or MD5 checksums. I tried to get rid of the SSL, but they don't let you do that. So the end result was just use the Python CLI, which uses C and C++ open SSL libraries and is very fast. This is solved in the beta version of Java, and if you have a new Skylake processor, but the cloud probably won't get that for a few years. The second limitation I ran into was kind of the stuttering as I was scaling up the cluster. And so in trying to figure out what was going on there, I ended up playing around with the Netty configuration options, which aren't yet in the Flink documentation. I'm hoping to add those. So the idea here was we get a few megabytes in our, by default, our Linux TCP IP buffers. So the idea was to boost that to 64. I'd also reduced the parallelism, the number of task slots per task manager. And the idea there was to boost back up the number of these arenas and number of threads that I was handing off to Netty. And that seemed to work pretty well until I went even further. And all I can say there is what didn't work in the evening worked the next morning. So that's just the cloud. You never know what's going on. And the last limitation was on these slow uploads. People have talked about it, the curse of the last reducer. And the answer here was, if it takes more than 120 seconds to download a file or 60 seconds to upload a file, we terminate that thread and retry it. So to do that, though, we have to persist our data and also limit the number of files that we're uploading. And it was fascinating. So when the first task manager finished, the job was 99% done. I was actually starting to get worried that the job was going to fail somehow. Okay, a couple quick things here at the end. So how can we improve Flink? So typically to profile Flink, I use this Java flight recorder. We can configure that within the Flink daemon. The issue here is we need to rotate the log file. So I treat it like a log file or the out files. I create a JFR file. And so I just edit my shell script there. The interesting thing is that we can actually concatenate our profiling. So if we have a cluster of task managers, we can concatenate the 60, we can combine, merge all the JFR files from each of those task managers, and we can see what's our profile across the entire cluster. So here's one example. I don't think either of us can see that. Of course, number one CPUs here is the normalized key sorter. So that's essentially the quick sort at the heart of Flink. This was probably on Jacquard index. We can see that our sorting is taking the most CPU that we're using. So where do we go from there? So the idea here is, I brought this up on the mailing list. The idea here is, well, what if we're able to compare two algorithms? So we write two versions of an algorithm. Let's take multiple samples and run at increasing scale, and let's just compare the two. So rather than micro benchmarking, which has this issue of we don't really know how that fits into the system, let's just run algorithms. Let's change our sort. Let's see, do we get a 1% or 5% improvement, and then pick whichever's best. So lastly, a couple features that are coming out. So Flink 3042, it's in review. So this kind of goes counter to Gabor's presentation on on code generation for serializers and comparators. So here we're actually hand coding serializers and comparators, but we're making it easy to do. So we annotate with type info, which points to a type info factory, which returns a type information. And that allows us to define our own serializer and comparator. So the idea here is, what I want it for is to efficiently serialize arrays. So there's some example code and an example type info. So what do we use this for? So we have our parallelized algorithms right now, and they can generate trillions of results. Oftentimes, we only want to know which vertices are most similar, or maybe the top k similarity. So we can do that if we can return a list. And then the second idea here is, can we switch over? Right now, we keep edge lists. Sometimes people write systems to keep adjacency lists, but can we do a hybrid where essentially we're processing the same list? We're processing each element multiple times, but we can store multiple neighbors under one key. And could we essentially reduce the number of keys by perhaps 100-fold that we're sorting and joining on? Another important feature is to be able to take iterations and take the output of an intermediate operator and use that somewhere in the program. This is impossible in Flink right now. I think it's a scheduler limitation. And this opens up a whole new class of algorithms for which typically we have many algorithms where we iterate, and the output of the iteration is the empty set. We're done processing. It turns out it's what we have in the middle that's valuable. And then this is kind of my crazy idea, though. I was talking to Gabor, and they're working on actually systems that kind of do this. But rather than requiring vertex and edge to be these concrete classes with a single value type, oftentimes we want to have multiple values stored on a vertex or an edge. But could we program to interfaces? And this would kind of eliminate this nested dolls that we have to pack in values right now. I don't know how you do that, though, because you're having to now map fields from input to output. Maybe the user doesn't even see those fields, but they're still being copied for that user. So anyway, why batch, why jelly? I think it's a great framework for building scalable algorithms. We have, I think, about 30 to 40 algorithms right now. I think this can scale into the hundreds. And I think it's a great out-of-the-box tool that users can take data they have, run the jelly drivers, and start seeing results immediately. Thank you.
Okay, time for some questions, short questions, because the closing session is going on. Right behind you.
Hi, thanks for your talk. Two quick questions. You mentioned that you had problems with the TCP buffer in Linux and that you had to change it. So just if you could repeat the reason, I didn't really get it. And the other one is, what did you use for profiling to pinpoint those problems?
So the two tools for profiling were Java Flight Recorder, which you can add to when you Java, and then you have all your Java parameters, and Java will record profiling as you're going along. And in this, sorry, I didn't mention this. This is Java Mission Control. You could probably see it online later. JMC. So this just comes with Java, and you can open up the output file of the flight recorder. The issue, so the TCP buffers, Linux will scale the read and write buffer size. So as you're pumping more data through your TCP connection, it increases that up to a maximum of, I think right now it's 3 or 4 megabytes. And by boosting that even higher, so we were pushing, I was seeing actually above 10 gigabits. We were pushing more like 12 gigabits. And it seemed that maybe increasing the buffer size, 12 gigabits is however many buffers per second. And if we weren't keeping those full, that might have been a limitation. So by increasing that to 64 megabytes, it seemed to run more smoothly.
Thank you.
Okay, anybody else?
May I ask you to say a few words more about the sort benchmark? How did you implement in a high level the algorithm sorting with Flink?
So I kind of went the easy route. I only did, they call it indie sort. So there's, I guess you guys would call it F1, I think is the way here. We call it Daytona and Indy, the stock car. And so indie sort, you ought to basically optimize in any way you want. So I created an indie record which had a 10-byte key and a 90-byte value. And I kind of took the TerraSort partitioner, I forgot what they call it now, but it's a tree-based partitioner, trie-based partitioner, and made that work not with the Hadoop text type, but made it work with byte strings. It was actually most of the work, very little of the work was actually done in Flink, making it work with Flink, and most of the work was kind of lassoing the 100 terabytes into Amazon and validating that.
Okay. Anybody else?
You mentioned cache awareness somewhere in your talk when you talked about the memory hierarchies.
Mm-hmm.
Are you aware of how Flink is doing in that area? Are we very cache aware, or is it something that has never been considered?
Yeah, I don't. Actually, I was talking with Stefan about this at lunch today. I don't know that there is a good way in Java to kind of monitor how many cache, what's our rate of cache misses, really other than just seeing if we're making changes and the runtime is improving, that we could probably ascertain that we're doing better on our cache. I think this Java object model where we kind of create objects all over the place. The objects tend to have a high level of overhead, and I don't have a good feel for where Java actually creates objects. Your cache is pulling in, say, 512 byte cache lines. Your objects may be scattered across multiple lines. Whereas with object reuse and working with simple types, or even, say, an efficient array type, we're hopefully working on the same chunk of memory consistently as we're reading in data and writing out data. So I think the goal there is to be much more, and I think Flink is already very much there, but if we can reduce the impact on cache misses, especially when we have 36 cores sharing a few megabytes of cache.
Okay. The closing session has begun. I guess we can all go there. Round of applause.